Good evening, everyone. Let me tell you, it is great to be able to share some thoughts and insights with you tonight on what I consider the defining challenge of our time, the global energy transition, and in particular, the challenge and opportunities this represents for the maritime industry. Before I start, I'd like to thank the National University of Singapore and especially Professors Zudong and Paul Long for hosting and establishing this fine lecture series. And I'd also like to recognize the work of Seatrium and their chairman, Mark Gainsborough, their CEO, Chris Ong, for supporting this series and their commitment to using their deep engineering capability to tackling shipping emissions challenges, and more importantly, making the solutions real. Let me start by saying the ability of shipping to develop a more sustainable industry is of enormous consequence to the world. This is because of the pivotal importance of the maritime industries to the global economy. It's so obvious that sometimes we don't actually stop to think about it, but just consider that about 11 billion tons of goods are transported by ship each year. That represents an impressive 1.5 tons per person. So why are we talking about shipping? Because I believe that shipping's capacity to transfer goods and materials from where they are produced to where they will be ultimately consumed is the foundation of modern life. And so I think it's fitting that we should begin this evening by in fact recognizing shipping's role as the cornerstone of which all future supply chains will be built. So this means that for our industry, and we'll talk about it this evening, the challenge and the opportunity lies in two stories. Shipping for shipping, which is the decarbonization of shipping, and also more importantly, shipping for the world, highlighting shipping's role as an enabler of the global green energy transition. These stories, as you'll see this evening, lead to many more stories and chapters. So where do we start? I'm going to try this evening to bring a lot of things together that really make up the shipping's decarbonization story. I'm going to try to answer essentially three questions. Where are we going? How are we going to get there? And what do we need to keep our eyes on? And at the end, I'm actually going to close with you, because we're going to talk a lot about technology this evening. But I will tell you, and I'm a technologist, technology has no sense of humor, no common sense, and no instincts. People, and more importantly, you, are going to be the real heroes going forward in the future. So let's start talking about how these pieces begin to come together. Let me just start this by saying, where does this story start? Well, it's already started. Shipping's journey to get to net zero by 2050 started in 2016 with the Paris Climate Agreement. That, in fact, represented a historic point in global environmental policy. The Paris Agreement's long-term temperature goal is to keep the rise in mean global temperature to well below 2 degrees Celsius or 3.6 degrees Fahrenheit. But preferably, we want to limit that increase to 1.5 degrees Celsius, because we recognize that this world that would actually substantially reduce the effects of climate change. So what does that mean for shipping? And we've talked about that. Well, shipping on one end transports 70% of the global supply. And in that process, it actually emits 3% of global CO2 emissions. Now, they've done a good job, but the reality is shipping is driven quite a bit by global seaborne trade, by economic development. So what we are worried about is in terms of absolute emissions, if we don't really begin to get our handle on the emissions of CO2 and greenhouse gas emissions of shipping, they will increase. And in fact, left without any action, that 3% will probably go up to 10% sometime by 2050. So that's our challenge. Our challenge is to begin to bring two parts together and to see how we can begin to reduce the CO2 and greenhouse gas emissions coming from shipping. So you're going to hear a lot today. We're going to be talking about a new language of shipping. We're going to be talking about what is the calculus of net zero by 2050 mean. We're going to be talking about CO2 and greenhouse gas emissions per ton mile. We're also going to be talking about dollars of CO2 and greenhouse gas emission reduction per ton mile. We're going to be talking about CO2 emission per transport work. We're probably also going to be talking about a whole new color scheme for those that aren't aware of it, of gray, of blue, of green, and of pink. We're in a really exciting time, ladies and gentlemen. We're really in the, if you think about it, in the early innings of a decade of change. We're talking about decarbonization as well as digitization coming together to probably be the two most transformative technologies that are going to affect us. We're talking about a new set of boundary conditions, safety, availability, scalability of fuels, and infrastructure. We're talking about new timelines. We're talking about a lot of very interesting things, even new relationships, new partnerships. We're not talking just about the ship. We're talking about the ship and the port. We're also talking about new public and private partnerships. So there is an awful lot going on as we speak right now, as we begin to prepare ourselves for this journey to 2050. Let me talk a little bit about where this starts. So regulations driven by the IMO, which is essentially an arm of the United Nations that is responsible for setting global regulations for shipping, since shipping is essentially a global industry, has already started to begin to address what are those signposts and outposts that we need to look at as an industry to begin making investable decisions to get us to where we want to get to. In 2018, what we saw was essentially the IMO put out their first essentially greenhouse gas strategy. That is the blue line. What you see there is that their initial targets were that by 2030, shipping would reduce CO2 by 40%. By 2050, they'd reduce CO2 by 70% and reduce total greenhouse emissions by 50%. But getting to net zero was not, you can see, was not by 2050. If you look at the trace of that blue line. In 2023, IMO came out with a second greenhouse gas strategy that really bent this curve and basically put us in the zip code of getting to net zero by 2050. Those signposts that everyone in the industry is locked in on right now is to reduce CO2 by 40% and reduce greenhouse gas emissions by 20% by 2030. They introduced an intermediate signpost by 2040, looking to reduce total greenhouse gas emissions by 20%. And then at 2050, they really were expecting the industry to get to the point where they could achieve net zero of all greenhouse gas emissions. That red line, which is what we're all working to right now as an industry, is basically what we are looking at in terms of outcomes and signposts. It has given us much great clarity, as you can see, the difference between the blue line and the red line. But I think, again, more importantly, and we'll talk about it today, it has given the industry an investable roadmap moving forward. In this process that support these regulations and this journey, and we're going to talk about how we're going to move down that red line, IMO has also introduced several markers on the table that are going to help guide us, to help us implement the programs and to hold us accountable as an industry to see how we actually drive change. And we're going to talk about a couple of them here. There's a lot, but the two that I think are the most important is the EEXI, which is the Energy Efficiency Index, and CII, which is a Carbon Intensity Indicator. They introduced some other things relative to well-to-wake emissions, and there's some things like market-based measures. But I wanted to bring these two out because these are the ones that I think really kind of begin to impact operations and design. Both of them are based on a relatively simple equation. In the numerator, it is CO2 consumption, and in the denominator, it is transport work, which is really, as you know, a function of capacity times range. And the way this works, if you are a ship owner or you look at the global fleet, the EEXI is essentially a one-time certification benchmark that kind of sets the playing field. And what happens is, as the industry moves forward, all eyes and attention are drawn on the carbon intensity indicator, because that is now going to be measured on an annual basis. And the industry and the ship owners are going to be required to report that and send it to the governments and regulators in order to be able to show whether they are in compliance. What has happened in this industry is the CII is not just a regulatory compliance mechanism. What we are seeing now is that banks, insurance companies, different parts of the industry are also embracing CII as part of either financial requirements, and if you are financing an asset, or if you're looking for a contract, let's say from a charter. Most important thing to take away is this indicator, this carbon intensity indicator, is going to bring the entire industry together, and it is going to be the mechanism that we are going to use to make the decisions that we have to make, whether it's how you operate a vessel, whether it's how you design a vessel, whether with the selection of what type of fuel, what type of technology for retrofits. All of it basically kind of boils down to this CII indicator. Very, very important. Kind of the last thing I want to say about regulations, and I'm spending a little bit more time on this than I would like, but one of the things that's happening is that regulations now are not just compliance requirements. They're actually becoming global shipping shapers. This is the first time we've actually really seen that in this industry. This regulatory framework that kind of ships are subjected to are going to have key elements. We've talked about that. They're going to have key timelines. There is a governance element, and the challenge for all of us is how to sync it, because not only do you have international requirements, which what I'm talking about here, which is IMO, but you have national, regional, and local. And the challenge for shipping is to bring all those together, because in the absence of bringing them together and syncing this up, this fabric will not work. And we have, in fact, international regulations. We have regional regulations, the EU, the US, China. Everyone is now stepping together. And so the challenge for the industry, aside from just what happens on the ship, is how do you bring all these regulations together to really provide kind of one synchronized roadmap for shipping with one timeline. So now let's talk about what is it going to take to get to net zero by 2050. I will tell you that when you look at the red line, again, that roadmap that came out of IMO in 2023. To get to 2030 is actually quite achievable. We have a pretty good clear line of sight. We know where we're going. Mark raised a good question. I don't know how many hands were behind me, but to get to net zero by 2050, at this point, and you'll see this over the course of this lecture, is at best directional. There is no clear line of sight for us as an industry to get to from where we are to net zero by 2050. Just a lot of pathways and a lot of work that has to happen. To give you a sense of the urgency of the problem and the magnitude of the challenge, I'm going to give you some statistics here. From a fuel point of view, in order to get to net zero by 2050, we will need a combination of probably 70% zero carbon fuels and 30% carbon neutral fuels in order to get us there. Now, 70% of zero carbon fuels means that we need to have 10 times more renewable energy than we have today. 30% carbon neutral fuels requires us to have 100 times more carbon capture capability than we have today. We'll get back to these terms and what they mean, but this is pretty significant when you look at what is defining the steepness of the curve. If I had to look at this from a macro level, not from a fuel point of view, but from a ship point of view, it would require that we would have to, on our current fleets and vessels coming in, we would have to reduce onboard carbon capture by 70%. We'd have to make enough improvements to reduce fuel consumption by 15%, and we would have to annually adopt at a rate of 5% new green fuels. Now, this is to get us to net zero by 2050. So I can tell you that although 25 years seems like a long time, the urgency is very real. Because when you start looking at those big building blocks that are required to get us there, which is availability and scalability of some type of carbon neutral or zero carbon fuel, married with the infrastructure to support a global industry that is the backbone of economic growth, you're talking about things that happen decades at a time. This doesn't happen overnight. That's why there is such a sense of urgency. That's why you see a lot of discussion. You see a lot of governments. Everybody now is coming together because commercial gravity alone is not going to get you there. It is going to require a new government industry partnership moving forward. So to get to net zero by 2050 is going to require, quite frankly, the entire energy system to be transformed using a wide range of technologies to, first of all, determine the future fuel mix of shipping, and second, to determine the right incremental and layering approach to address the existing fleet. Because there are a lot of ships out there. So whereas you talk about the discussion of what are new technologies for new ships that are going to be ordered, that are going to go out in the fleet, you have a lot of vessels that are in the water right now that have to also begin to comply to these requirements. So we're going to try to pull all this together in the next 30 minutes, and I'm going to try to give you a little bit of a glimpse of the complexity of the challenge, but I think more importantly, introduce you to what I think are the key transformational technologies and the opportunities. Because as you know, wherever there are challenges, there are opportunities. And we want to talk a little bit about that. If you look at this problem, not from this perspective, which I just talked about, which I call the macro perspective. If you looked at this problem from what I call the deck plate perspective, in terms of what is out there today, this problem basically is broken down into what I call a 70-30 solution. Yes, 70% of the solution to get us to net zero by 2050 is the fuel, or are the fuels. And there may not just be one as we have today, but 15% has to do with looking at retrofits and bringing in new energy efficiency technology on board the vessel. And the other 15% as to how we use data and data science and data analytics to help us optimize the performance of the vessel. So what you see on this slide is that 30% of the ability for us to develop a solution, it's not a dimensional solution, it is a hybrid solution, is in our control. And we'll talk about what I will try to do over the course of this evening is break out what's in the 70% bucket, what's in the 15% bucket, and what is in the other 15% bucket relative to data. Because for all the engineers are out there, what I'm going to tell you is that the exciting part is when I was growing up, shipping was basically a relatively simple single point design. Now you're looking at multi-point optimization. When I was growing up, when I was a naval architect, it was pretty easy. You design a ship for one speed, one draft, and that impacts the whole shape, the bow, and the engine capacity. What you're going to see now is we are moving into a dimensional world. And it's going to require an awful lot of technology. It's going to require kind of to rewire some of our decision-making to be able to make those right decisions that are going to impact us. So now let me move over to and continue my deeper dive and actually talk about what's behind the 70-15-15 kind of hybrid solution. And we're going to talk about fuels, we're going to talk about ship technologies, and we're going to talk about transitions and timelines. Ships today currently run on heavy fossil fuel. Okay? There's a C. A little bit of this story will be about molecules. There is a C in that fuel. As we look forward and as we look at what are those options and what are those fuel types available that could help this industry moving forward, what you see on the slide, it's not so easy. There is a lot of criteria that we have to meet. We have to address availability, scalability, and affordability of fuels. We have to address the infrastructure. Is it there to provide the fuels for the vessels? The bunkering stations, which are basically kind of global gas stations, if you can imagine, pre-positioned all around the world, of course, of which Singapore is one of. And it's going to require an understanding of safety. In other words, making sure at the end of the day, as we move into this new generation of potential fuels, we understand the unintended safety consequences of change and of these fuels. The fuels that we are looking at right now as an industry, and this is in the early phase, and I will tell you that as we look at this problem and begin to push it out, you will see there is a short game, a mid game, and a long game. But what we see right now are LNG, which is methane. For those of you, I flunked chemistry, so I had to look this up. For those of you that know the molecular equation of LNG, it's CH4. There's a carbon atom in there. We have methanol, which is CH3O. We have ammonia, which is NH3. And of course, we have hydrogen, which is H. We also have biofuels, which we can look and put into this mix. But this is kind of where we're starting from, with no clear-cut single answer. And we'll talk a little bit about this. But this is basically what the industry is beginning to look at now relative to the options relative to heavy fuel that we have in front of us. Just a little bit more information on the fuels. you can see in this chart, I picked out a couple of comparisons and markers because a lot of this, for example, boiling point impacts containment systems. Obviously, safety is going to be really important, not just on the vessel, but when the vessel comes into port. We talked about infrastructure, and what I wanted to talk a little bit more, I hadn't brought this up yet, is not just tank to weight emissions, but also weight to well, because IMO now is moving this discussion of fuels past the engine room. It's past what in the industry, the tank to weight piece. They are now challenging the industry. You got to pick a fuel that goes from basically well to weight. So as we look at this compliance requirement, the fuels, in fact, the greenhouse gas emissions and CO2 reduction is not just what's on the ship that the ship is emitting. It is what is happening in that whole process to produce that fuel, bring that fuel to the ship, and that is going to be what we call well to weight. And then what I did here is also begin to get a sense of what is the cost in terms of impact on shipbuilding. Again, to give you a sense of readiness and timelines. And I will say, by the way, before I go back, in the shipping industry, one of the big indicators for types of fuels used are the engines. Now, in the case of LNG, there are engines that burn LNG. In the case of biofuels, or in the case of methanol, you can actually use the current combustion engines. But when you get to ammonia and when you get to hydrogen, those engines aren't available. The first ammonia-fueled engines that are being developed right now will come into the industry at the end of 2025. So we can talk a lot about ammonia. It's not there yet, but it's coming. So when you look at this dynamic relative to ships, you've got to look at this, in a couple different ways in order to begin to understand readiness, because that's what this is all about: understanding readiness, understanding technology readiness, trying to make the right decision, understanding those three boundary conditions, those swim lanes that we all have to work towards. And the reason why I said that is because if you look at the well to wake characteristics of fuel, and I bring this up, the picture changes a little bit. For example, if you see all the way on the right side here, you have ammonia and you have hydrogen. So the blue piece is the piece that's basically outside the ship. The red piece are the emissions on the ship. So in the case of ammonia, and in this case hydrogen, you see no red. That's because there's no carbon atom. But when you look at the blue piece, which takes it all the way back from the beginning, from production, all the way to getting it to the ship, it actually, that process burns and emits, more CO2 and greenhouse gas emissions than the column all the way over to the left, which is basically heavy fuel. So the ammonia and the hydrogen currently today are what we call gray. They come from fossil fuel. Okay. And the challenge is, how do we make all this work? Okay. And we will talk about ways like carbon capture, which is extracting carbon from some fossil fuel activity. And we'll look at kind of these generations of how these fuels can kind of reconfigure themselves. But, I'll be talking a lot about gray, blue, green, and pink. Gray are fuels that originate from fossil fuel. Blue are fuels that originate from fossil fuels where you use carbon capture and extract the carbon atom. Green fuels are the fuels that you generate from renewable energy, whether it's offshore wind or solar. And that is ultimately where we as an industry want to go. And that is why it is so important for us to figure out how to get there. And that is why that challenge is that you saw in the calculus equation is we need 10 times more of that capacity in order to begin to help the shipping industry solve their fuel issue. The reason why I bring this up is because if you are a ship owner, not only in addition to the requirements of compliance based on a technical equation, the regulators now are enforcing cost of compliance or market-based measures or dollars. So you're now also going to be paying penalties. And the penalties are focused on the life cycle performance of the fuels. Pretty interesting stuff. We're just getting started here. Just to give you a sense, again, I'm going really, really deep, but to give you kind of some sort of sense of what this industry is wrestling with. If you were to order a vessel today with conventional fuel, per the requirements, that vessel can go 10 years without any sort of rating change that would cause you any sort of compliance problem. If that same vessel was ordered with LNG, you could go 20 years. And if you used methanol, you could go 15. The reason why I'm telling you this is because from an engineering point of view, in terms of how to begin to get your arms around making that decision going forward, there are a lot of levers that you can use and a lot of things at your disposal that helps you begin to optimize this problem, not just in terms of regulatory compliance, but also in terms of technology readiness. And I'll add one more dimension. Risk. And we'll talk a little bit at the end about risk. What I've attempted to do here is to give you a sense of what is the risk profile of these fuels today. Of course, the challenge is this risk profile needs to change by 2050. You need to get more green in there than red. But you can see everything is baselined off the top, which is fossil fuel. And you look at those, everything from fuel production to storage, logistics and bunkering, onboard fuel conversion, onboard safety and regulations. Man, we know how to work with fossil fuels. Not a surprise. We've been doing this for a long time. When you start looking down, you will see the biggest risk challenges and the biggest gaps are with the fuels that do not have a carbon atom in there. Hydrogen and ammonia. That's the challenge. So you really begin to understand kind of from a risk versus risk point of view relative to everything going on, how this all kind of shapes up, and then what are those things that we need to do to begin to manage and mitigate this type of risk. And I will just point out one thing, and specifically, let me just talk a little bit about ammonia safety. Okay, probably toxicity of ammonia remains, I think, the defining safety challenge of this fuel. And I think if you were to look into the literature, any dosage of 300 parts per million, if you breathe in any of that, it's harmful. And even as low as 35 parts per million, if you were exposed to that, that would be dangerous and certainly unpleasant. So, but we have the ability to understand this and begin to see what can we do to put a fresh focus on safety in the case of ammonia. Listen, we can put a man on the moon. We can clearly begin to understand what is going on with ammonia and begin to understand what does that new safety environment look like, both on the ship, in the engine room, as well as at the bunkering facility outside the ship. And so what you see here are just two examples of using simulation and visualization technology to help us understand the ammonia safety problem. And on the left side, and by the way, this technology, this simulation and visualization technology actually originates here in Singapore. You have a very, very good Singapore simulation center and a real commitment to, again, use that and extend that going forward. We actually, in my company, use this technology. But on the left, what you see, and I won't get in a lot of detail, but what you see is essentially a dispersion model of an ammonia leak in an engine room, because it will help us to understand where is the right location of sensors, what is the right design of ventilation systems. On the right-hand side, we are looking at dispersion modeling. What does how does an ammonia plume react to certain weather and wind conditions outside? And how do we best, if you do have a plume, organize our emergency response? So this is a solvable problem. Like everything else with these new fuels, it's a challenge and is going to require a new approach to thinking, and it's going to require all of us to really use the technology that we have available to help us understand this. And in this case, remember, one of those boundary conditions that I talked about, there's 3 of them, is safety. Safety, safety, safety. What are the unintended consequences of change, especially related to safety? And in this case, this is a good example of what we see and what we're working on. So that's a little bit about that 70% bucket. I've got 2 slides. Let's talk about that 15% bucket of energy efficiency, that low-hanging fruit. And what I just want to show here is that modifying existing vessels to improve CO2 and greenhouse gas emissions, in fact, can be done. And you see, you have, quite frankly, a whole portfolio of technology that you can apply today, everything from using whole form improvements to improve, reduce resistance and improve propeller efficiency, to renewable energies, to like batteries, to looking at minimizing onboard energy consumption, machinery optimization, and electrical energy storage. And then let me just go right into the data piece, which is also very exciting, and it's very, very important, is how do you bring data into this picture, and how, from a vessel point of view, based on voyage performance and voyage optimization, you can either at a systems level improve the CO2 reduction in greenhouse gas emissions by the combination of speed and performance, as well as on the left-hand side, how to use sensor information to actually tune a machinery component to help you out. So 70, 15, and 15, 15 and 15, or that 30%, is something that can be used today. I'm going to move through this relatively quickly because I see I've lost a little bit of time here. Let me just tell you a little bit about a glimpse of the future. In our outlooks, we're over on the left-hand side. You can see the blue is dominated, quite frankly, by oil-based fuels. But what you can see is, based on our assumptions, as you move towards 2050, you're going to see a new fuel mix. That new fuel mix is not going to be dominated by oil. It's going to be, on the right-hand side, about 21% oil, about 11% LNG, a little over 1% LPG, 40% methanol, and 28% aluminum and hydrogen, ammonia and hydrogen, excuse me. So you can see how that mix is changing. I'm going to run through 3 slides and close this thing down real quickly. But what I do want to leave you with is, as you look forward, what's very, very important is you begin to look at the types of fuels on the vessels, and you begin to look at how do you get there. What will happen is there are 3 value chains that are emerging that are really important, because these value chains are not only going to drive, quite frankly, the type of fuel you put on ships, they are going to drive economies. And I would suggest, if you Google, you will see Morgan Stanley, Goldman Sachs, any of the big banks, they actually talk about the new economy, the new carbon economy, the new ammonia economy, the new hydrogen economy, how that moves forward. And the exciting thing is that shipping now, we talked a lot about how to reduce CO2 emissions of ships. Shipping now is going to be carrying ammonia and hydrogen to support government clean energy transition programs. They're going to be carrying liquid CO2 that is going to be pulled out through carbon capture and store it somewhere. And this is also going to generate economic value. And it's really, really important because shipping is going to be a big enabler in this process. That's all I'm going to say about that because I'm running out of time. So what I really want to do is get to the very end here. I want to talk just a little bit about transformational technologies because it's not just what's in the engine room and in the combustion engine, but I want to throw out two terms for you to keep an eye on: electrification and nuclear. Nuclear is very interesting because nuclear, quite frankly, you have a whole new generation of small modular reactors that are completely different from what I think we all grew up with, at least what I grew up with. On the left, you see kind of the reactors that you would see if you mentioned Chernobyl, okay, where the water is a coolant, you have a very highly enriched uranium fuel. But on the right, you have a whole generation of the microreactors where the salt is the fuel and the coolant. And when you look at passive safety, and when you look at this from that point of view, opens up a lot of opportunities. And the nuclear story is actually two stories. It's not the reactor that goes on the ship. From a propulsion point of view, a lot of activity about putting nuclear reactors, these small advanced reactors, in this case, I'm showing you a molten salt reactor, on a barge, on an FPSO somewhere to generate pink hydrogen to be able to feed into a city's electrification power grid. So I wanted to share that with you. And the only thing I want to mention before I close is not to discount the other big transformational technology that's out there in addition to decarbonization. It's digitization. It is autonomy. It is artificial intelligence. It is using digital twins to help us understand and predict response. These are things that are also very transformational and are going to be a part of the solution. So let me close by focusing this back on all of you, because I think this is really, really important as I close this. And the questions that I'm closing with is: one, how do we turn challenges into opportunities? What do we do when the problems are real, the stakes are high, time is short, and abstract answers are inadequate? What is the real chemistry for success? And what is the real fuel of the future? Let me just start by talking a little bit about risk, because this is going to be a mindset for all of you as you move into this area, into these early innings of a decade of change. You need to be able to be comfortable and to embrace risk. And it's not just risk, it's actually dimensionally risk versus risk. I've put this chart out here because I think it's actually very good. I actually show this to my entire leadership team in my company. It's taken out of a book by two Harvard professors. But the theory here is if you have a risk, you always have a countervailing risk. And if you go all the way down to zero on this XY axis, that is the probability that that risk will occur, both of them. And as you move across the x-axis, as you move up the y-axis, those risks basically mitigate themselves. They diminish, as you can see. The probability of risk or the target risk or the countervailing risk goes to zero. The point I want to make, and this is important, is there is a mathematical line that connects both of those risks, and that is the risk protection frontier. And if you move that out, you begin to manage your risk, whether it's a safety risk, whether it's a commercial risk. And the way you move it out is either through resources, through technology, through innovation, or through policy. Very, very important. Closing this thing out. Talk about people. Let's talk about everybody in this room. For those of you that are studying, let me tell you, the talent equation is changing. When I was in school, when I was your age, the talent, that the ability to develop talent, that talent equation was based on age, experience, and training. Now, when you look at decarbonization and digitization, that equation is changing. It is about skills. It is about continuous learning. It's about systems thinking, similar to the risk versus risk slide I had. But the key here is continuous learning, the ability to continually become continuous learners. That's very important. For all of you in this room that are students, as you move into the into work and into the corporate environment, employers will value continuous learning. The reason why it's important is because you are moving into an era where technology is changing pretty quickly, and you've got to be able to adapt. Second to last slide. Success is a team sport. I told you commercial gravity is not going to get us there. You're going to see a whole new generation of public-private partnerships. You're going to see a whole new generation of working together. It's very interesting because prior to these regulations, I'll just use a port. Port inefficiencies did not impact ship efficiencies. But now, since the requirements require and watch ship inefficiencies relative to CO2 and greenhouse gas emissions, ports become part of that problem or part of the solution. That's why you're going to see a tremendous amount of investment moving towards new infrastructure, different ways of looking at ports. You see this actually in the literature, but you see things like clean marine hubs or green corridors. You're going to see this. So this is not going to be done it's going to take a village to basically solve this problem. Pretty exciting stuff. Let me just close by saying, at the end of the day, people working together, embracing change and uncertainty, learning to make innovation their friend, and managing risk decisions based on data is going to be the jet fuel that we need to get to net zero by 2050. This is your challenge and opportunity. I've mapped it out tonight. Meeting this challenge basically is going to require all of us working together, but more importantly, it's going to be about you going forward. The training you receive here at this university is going to be important and, in fact, critical in equipping you with the skills that you're going to need to deliver on the decarbonization promises that we are making today. There are tools that we need. You've seen some of these, but what I'm really saying is at the end of the day, we are relying on you. And this is a great opportunity to really be the quarterback relative to not only a new mindset, new technologies, new ways of thinking, moving forward to help us collectively solve this problem. So no pressure. No pressure. Piece of cake. You are the answer to get to net zero by 2050, by the way. So with that, I just want to thank all of you for spending a Friday evening with me, and we're counting on you. Thank you very much.